Hello everyone. In this video I'm going to be going over I think 4 examples I have set up in which I'm going to be solving differential equations by the method of undetermined coefficients, specifically using something called the Annihilator approach. Now hopefully you've seen a previous video of mine on annihilators and what those are and what kinds of linear operators annihilate certain types of functions. It talked about polynomial functions, exponential functions, and trigonometric functions. So let's get into them. All right. So same instructions for every single example. Solve the given differential equation by undetermined coefficients using the annihilator approach. So my first example is y double prime, the second derivative, minus 9y equals 54. Alright, so step 1. Right now, this equation is it's second order. Right, it's a second order equation. It's linear, right? The coefficients of y and y double prime are constants, actually, right? So it's definitely a linear. But the constant term without y or y prime attached or anything like that is not 0. So this is a non-homogeneous differential equation. All right, so in this case, I take all my y stuff to one side and then non-y stuff to the other. We see it's non-homogeneous. So the first step in the annihilator approach, or really solving any equation by undetermined coefficients, is to solve the associated or corresponding homogeneous equation. It's DE, differential equation. Now this is simply, again, with all your y's and y primes and everything involving y on one side, everything that doesn't involve y on the other. To make the associated homogeneous differential equation, you just basically write the same equation, but make the constant term 0. Just make the other side 0, not the constant term. But so y double prime minus 9y equals 0. Now you've done this hopefully before, or you've seen videos where I've done something like this before. This is a second order linear homogeneous equation with constant coefficients. So I could do one of two things. I could let y equal e to the mx and find the auxiliary equation or characteristic equation and solve that and state my general solution to this. But if I write using operators instead, I'm going to use, think about annihilators. Right? I'm going to think about annihilators. Writing using operators, right, that d representing derivatives, this would be the second derivative, d squared, minus 9. That'd be this operator applied to the function, some function y. And when is that equal to 0? Right? So basically the question is, what kinds of functions would d squared minus 9 annihilate? So d squared minus 9 annihilates, right, turns into 0. Annihilates, what functions? What kinds of functions? Well, d squared minus 9, that's a factorable expression. That factors to d minus 3 times d plus 3. So I have this operator applied to some function y is equal to 0. And if you recall from, a previous video of mine or from whatever textbook you're reading that has the annihilator approach, annihilators mentioned in it, d minus 3 annihilates e to the 3x. And d plus 3 annihilates e to the negative 3x. And being that I have the product of them together, their product annihilates then any linear combination of these two. So we get our general solution here to this homogeneous equation, which is sometimes, since it's not the actual original equation itself, it's a complementary equation. Very often then they're going to call this solution to the associated homogeneous equation the complementary function, or the complementary solution. They're calling, they label it usually y sub c for complementary. And the general solution, this complementary function, the general solution to this associated homogeneous equation is any linear combination. So say c1 times e to the 3x plus c2 times e to the negative 3x. Right. So this isn't the final answer. This is just going to be part of the answer later. Okay. So that's step one. Solve the associated homogeneous differential equation. Step two is going back to the original non-homogeneous equation. We're going to apply an annihilator, basically the annihilator of this side that makes it non-homogeneous. We're going to apply an annihilator to both sides of the original equation. You'll see what I mean. So hopefully you recall this, that so I got y double prime minus 9y equals 54, which, as before, I can write this using the linear differential operator as d minus 3 times d plus 3, right, applied to y. That gives me this side equals 54. Now hopefully you recall how the general solution of a non-homogeneous equation looks, right? Remember, the general solution of a non-homogeneous differential equation looked like the following. Y equals, now it's going to be this complementary function that we found earlier, right? The solution to the homogeneous, plus, and then what a lot of books will label y sub p. All right, now this y sub p is a specific or particular solution to the non-homogeneous equation. So this is any specific or particular, particular solution to the differential equation. Right, so this yp is not going to involve generic constants like yc does. Yc here, the complementary function, the solution of the homogeneous, involves these, these c1 and c2, these generic constants. Yp will not involve any generic constants. We'll have to find the values. All right, so writing it in terms of differential operators, now I have to think what operator annihilates this right side. So what linear operator, linear differential operator, annihilates just 54? Well, that would just simply be d, right? The first derivative of 54 would be 0. So I'm going to apply d to both sides, and we get the following equation. So we'd have d times d minus 3 times d plus 3. This operator now applied to y equals, and then applying d to 54 is 0. And now I have pretty much another homogeneous type equation, right? So I kind of transform a non-homogeneous into a homogeneous. And then we think again, where I'm trying to solve for y here, what kind of functions are annihilated, right? Because we have this operator applied to y as 0, so it's annihilated. What functions are annihilated by this operator, d times d minus 3 times d plus 3? Okay. Now, remember, d annihilates 1. That's it. D annihilates any constant, really. And I mentioned earlier, d minus 3 annihilates e to the 3x, or any multiple of that, any constant multiple of e to the 3x. D plus 3 would annihilate e to the negative 3x. And we have their product. So their product would annihilate any linear combination, right? Any linear combo of these three. So what I'm getting here is that y here would need to look like the following. Some constant times e to the 3x plus some constant c2 times e to the negative 3x, and then plus some other constant, say c3 times 1, but no need to write times 1. All right, so look at this, This constant times e to the 3x plus another constant times e to the negative 3x, that's the complementary function from earlier. That's this yc, the solutions to the corresponding homogeneous equation. So then the rest of it, right, the rest of it, c3, this is the form that the specific solution, the particular solution, will take. Right? This is actually going to be the form of yp. Now remember I said earlier, yp, the particular solution, is not going to have any generic constants. So what I need to do now is actually find a value for c3. Right? So that'll be part 3. Right? Find a specific yp. And this is using the differential equation itself, right? So we know that yp, right, a particular solution to this equation, is of the form, just some constant. Now you can use c3 still, or you can change it, in some book, in the book I'm looking at, they change it to, a or something. But just know that c3 is and then I want to find the specific value of c3. Well, the differential equation, again, looks like this, right? Here's the d one more time. Y double prime minus 9y equals 54. And, yp prime would be 0, so then there, yp double prime would definitely be 0. And I sub these, into the differential equation, and I solve for c3 to get a very specific particular solution. Right? So I have what? 0 minus 9 c3 equals 54. So c3, this constant then, this particular solution, is just negative 6. All right, so the particular solution we're looking for is yp equals, or just y equals negative 6. And then finally, I can form the general solution of our non-homogeneous equation. And remember, it looks like this. Y equals, your complementary function plus the particular solution that we find. So the general solution to this equation looks like this. Y equals some constant times e to the 3x plus some other constant, c2, times e to the negative 3x, and then plus, C3, which was negative 6, so minus 6. And I would leave it to you to verify this. Take this family of functions here, take the first derivative, the second derivative, and substitute things, and you will indeed get a true statement. You will get, 54 equals 54. I promise you that. All right. Wonderful. All right. So that, again, these four parts of the process: solve the corresponding homogeneous, then go back to the non-homogeneous, annihilate one of the sides, apply an annihilator to both sides, find the form of the solution of that equation. Part of that form should be the complementary function, and then the other part will be what the particular solution looks like. And then you need to take that particular solution and find, what specific solution are we talking about, and then you can form the general solution to the original equation. All right, lots of stuff. I'm going to do this 3 more times. All right. All the same steps. Right, let's do that again. So here I have a third order equation that's, again, non-homogeneous because of this 8x squared on the right side. I got y triple prime, right, third derivative, plus y double prime equals 8x squared. Now, using operators, this would be d cubed plus d squared, right, applied to some function y on the left side here. Right. It's the third derivative of y plus the second derivative of y, right, equals 8x squared. All right, so first part, again, the associated homogeneous equation, right, which would be just, d cubed plus d squared applied to y equals 0. And we got to think about what kind of functions, what could I replace y with that would actually be annihilated by d cubed plus d squared. Now, if you factor d cubed plus d squared, you'd have d squared times d plus 1. That operator applied to y equals 0, annihilates y. And again, hopefully from other whatever reading you're doing or a previous video of mine on annihilators, right? D squared annihilates d squared annihilates 1 annihilates constants and x, right? So d squared annihilates any linear function, right? And then d plus 1 annihilates, e to the negative x and any multiple of that. And this is, their product. So d squared times d plus 1 annihilates the following, y, and this is going to be the complementary function, right? The solution, the general solution to this associated homogeneous equation. Y equals, some constant, say c1 times 1, plus some constant c2 times x, and then plus some constant c3 times e to the negative x. All right, so there's the general solution to this, if you wrote it out like this, y triple prime plus y double prime equals 0. There's the general solution, right, or this complementary function to that homogeneous equation. All right. All right. So the next part, where I apply, annihilators. An annihilator, the annihilator of 8x squared. All right. We have again, I'll write it out with the differential operators. We have d squared times d plus 1, right, applied to some function y equals 8x squared. And 8x squared is annihilated by d cubed. Right? The third derivative of 8x squared would be 0. All right, so then I apply d cubed to both sides, giving me the following, kind of like homogeneous equation. Now if I apply d cubed, this becomes d to the 5th times d plus 1 applied to some function y equals, and then applying again d cubed to 8x squared annihilates it. And then just like earlier, I have to think, what functions are annihilated? What does this y need to look like? What kinds of functions are annihilated by this operator, d to the 5th times d plus 1? Well, d to the 5th annihilates the following. It annihilates, a constant, x to the 1st, x to the 2nd, x to the 3rd, all the way up to x to the 4th. So basically any 4th degree polynomial is annihilated by x to the 5th. Or sorry, d to the 5th. And as I mentioned earlier, d plus 1 annihilates e to the negative x. So y here looks like the following. Now there's a reason I'm going to write it this way. I'm going to have some constant, times 1 plus some constant c2 times x plus some constant c3 times e to the negative x. Again, there's a reason I'm writing this, is because this is the form that our complementary function took, right? The solution of the associated homogeneous equation. Then the rest of it, I used 1x and e to the negative x. The rest of it, some constant times x squared plus some constant times x to the 3rd plus some constant times x to the 4th. The rest of this is the form that a particular solution to this equation takes. And I need to find these constants, the C4, the C5, the C6, which, just so I can save on writing, I'm going to call these capital A, capital B, and capital C. All right, so YP is, the form a particular solution takes is ax squared plus bx cubed plus cx to the 4th. All right. And this brings us to part 3, right? Finding this particular solution. What are the values of a, b, and c that give me a specific solution to this differential equation? All right, well now the differential equation, remember, I'll write it again here. Third derivative of y plus second derivative of y was equal to 8x squared. All right, so I need the third derivative of this yp, the second derivative. All right, so yp prime would be 2ax plus 3bx squared plus 4cx cubed. The second derivative would be 2a plus 6bx plus 12cx squared. Then the third derivative would be just 6b plus 24cx. Then I substitute these into the equation. And on the left side, we're just adding the third derivative and second derivative. So I'd have what? 12c, the x squared terms, 12cx squared. Adding the x terms, I'd have 6b plus 24c times x. And then adding the constant terms, I'd have 2a plus 6b. Right, and this needs to be equal to 8x squared. So I have a polynomial on the left, polynomial on the right. The only time polynomials are equal is for all x, for all inputs, is when their coefficients are the same. So then I equate coefficients, and we get a little system here. So the 12c, the coefficient of x squared on the left, needs to be 8, right? The coefficient of x squared on the right. So 12c, so I'm getting like a system here. 12c needs to be equal to 8. the coefficient of x needs to be 0, so 6b plus 24c needs to be 0, and then the constant term also needs to be 0. 2a plus 6b must also be 0. Alright, so from this equation, c is going to be 8/12, which is 2/3. And then from this equation, we'd have 6b plus, 24 times c. Well, that's 24 times 2/3. And 2/3 of 24 is 16 equals 0. And then from this we get, subtract 16 divided by 6. Be negative 16/6 or negative 8/3. Right? B equals negative 8/3. And then in this last equation we'd have 2a and then 6 times b. 6 times negative 8/3 would be negative 16. Right? And then that's equal to 0. And then solving for a, we get 8. So now I have the form for our particular solution. yp equals 8x squared minus 8/3 x cubed plus 2/3 x to the fourth, right? It was ax squared plus bx cubed plus cx to the fourth. All right, going back here. Right. And that's not it, though. Now that I have found a specific, particular solution to this equation, and I know the solution, the general solution to the corresponding homogeneous, I can now state the general solution. Right? This was part 4. I can now state the general solution of our original differential equation is y equals, again, some constant c1 plus, let me go back here, this plus c2 times x plus c3 times e to the negative x. Right there was the complementary function, and this is for any constant c1, c1, c2, and c3, plus our particular solution 8x squared minus 8/3 x cubed plus 2/3 x to the fourth. And I'll put that in a big bubble. Right? That's the end. And you can go and verify this. There was the differential equation. Take this giant y here, take the first derivative, take the second derivative, third derivative, plug them in, and you'll verify, hopefully, that indeed this type of function for any value of c1, c2, and c3. Right, go ahead and replace c1, c2, and c3 with anything. This function will be satisfying that differential equation. Okay. And just a couple more of these. And hopefully, again, you remember your annihilators. Alright, so this one I'm going to kind of go a little quicker. So if I write these as with operators, this would be d squared plus 6d, right, first derivative, and then plus 9 applied to some function y equals negative x times e to the 4x. Now, looking at the homogeneous, we'd have, and then factoring this would be what? D plus 3 squared, right, that operator applied to y equals 0. And we can get our complementary function from this. What kinds of functions are annihilated by d plus 3 squared? Right, d plus 3 squared, remember, this annihilates, first off, e to the negative 3x, but also with the second power on there, it'll also annihilate x times e to the negative 3x. And then, any linear combination of these. So that's our complementary function. yc equals, some constant c1 times e to the negative 3x plus some constant c2 times x times e to the negative 3x. All right, and then then I would like to go back to the original and apply the annihilator of this side that makes it non-homogeneous, the side with negative x times e to the 4x. And what would annihilate this would be d minus 4 squared. Right? The operator d minus 4 squared would annihilate this. Right? Annihilates. All right. And then I apply this to both sides. So applying annihilator, applying the annihilator gives me the following. We'd have d minus 4 squared times the d plus 3 squared from earlier. Right? This applied to some function y equals 0, because I annihilated the right side. All right. Well, as mentioned, d plus 3 squared annihilates these. Now d minus 4 squared, this annihilates the following functions. It would annihilate e to the 4x and x times e to the 4x. All right. Now I've already got yc from d plus 3 squared, so this will give me the form of yp. But let's take it here. From here we get y equals, yc, right, these guys, plus, and then some linear combination of e to the 4x and x times e to the 4x. So I'll call it a times e to the 4x plus b times x times e to the 4x. And this is the form of yp, right? The form of yp. I'm not done. I need to find this a and this b. Right. So let's take the form of our particular solution, take the first derivative, second derivative, plug it into our equation, and solve for a and b, and then we'll be done basically. We can state the general solution. So again, yp has this form, a times e to the 4x plus b times x times e to the 4x. And then yp prime would be, 4a e to the 4x plus, I got some product rule here, 4b x e to the 4x, and then plus b times e to the 4x, and you can combine some like terms here. So we have the quantity 4a plus b times e to the 4x plus, and then 4b x e to the 4x. All right. And then the second derivative, again here this would just be 4 times this, 16, so 16a plus 4b e to the 4x plus, and then some product rule here. So 4bx, and then 16bx e to the 4x plus 4b e to the 4x, and then combining some more like stuff, the e to the 4x terms, I end up with this 16a plus 8b times e to the 4x, then plus 16b x e to the 4x. All right. Now, putting these expressions into the equation up top would give me the following. Now, I'm going to focus on I'll focus on these x e to the 4x terms first. All right, and then I'll focus on just the e to the 4x terms. So we have y double prime, so 16b x e to the 4x, plus 6y prime, so plus 24b, which would be 40b plus 9y. So we have 49 bx e to the 4x plus, and then now I'm going to focus on the e to the 4x terms in each of these. So y double prime, which is 16a plus 8b, 16a plus 8b, plus 6y prime, so plus 6 of this. That'd be 24a plus 6b, and then plus 9y, so that's plus 9a. So putting these all together, we'll have 49a plus 14b e to the 4x. And this needs to be equal to, negative x e to the 4x. All right, and then I equate coefficients of like terms. So 49b here, this coefficient of x e to the 4x needs to be negative 1. And the 49a plus 14b needs to be 0. All right, so from this first equation, b is clearly negative 1/49. And then plugging that in here, we'd have 49a, then 14 times negative 1/49 be negative 14/49 or negative 2/7. Right. And this needs to be equal to 0. And then from this we solve for a, it'd be 2/7 times 1/49. 63, 343, 2 over 343. Right. So the particular solution is, 2 over 343 times e to the 4x, then minus 1/49 times x e to the 4x. And now I can state the general solution. So then putting these together, right, the complementary function and this particular solution, right, the general solution to this differential equation is, let's see, the complementary function was, some constant c1 times e to the negative 3x plus some constant c2 times x times e to the negative 3x, and then plus our particular solution that I have found here, plus 2 343 times e to the 4x minus 1/49 times x times e to the 4x. And that's it. Right? And you can take this, take the first derivative, second derivative, plug it into the original differential equation, and you will see that it does indeed work. And I will leave that to you, of course. That would take a long time to do here. All right, and then I've got one final example of applying this Annihilator method to solving a certain non-homogeneous equation. So again, I'm going to run through this a little more quickly. This is d squared minus 2d plus 5, all right, applied to some function y. And first I'll look at the homogeneous equation that's associated with this, equals 0. All right, so what kinds of functions are annihilated by this? Now this is not factorable. All right, I'll tell you right now, this is not factorable. So I'll leave it to you to determine this, but this, I'll tell you right now, d squared minus 2d plus 5 annihilates the following functions. Annihilates e to the x times the cosine of 2x, and would annihilate e to the x times the sine of 2x. So therefore, it'll annihilate any linear combination of those. All right, this is just based on, because I know my annihilators pretty well. If not, if this isn't familiar to you, look at the homogeneous equation over here. and let y equal e to the mx, and then you'd have, the auxiliary equation m squared minus 2m plus 5 equals 0, and this would be m squared minus 2m plus 1 equals negative 4, and then you got m minus 1 squared equals negative 4. So m equals 1 plus or minus 2i, and you remember the solutions, the fundamental solutions coming from such complex conjugate solutions to the auxiliary equation would be e to the x times cosine 2x and e to the x times sine 2x. Right. So if you don't recognize the annihilator, you can always solve the homogeneous equation with these constant coefficients the way that I have in the past with in past videos with the auxiliary equation. Okay, so the complementary function, the solution to the corresponding homogeneous, would be some constant c1 times e to the x cosine 2x plus some constant c2 times e to the x sine 2x. All right. Now, this side. All right. The annihilator of e to the x sine x would be d squared minus 2d plus 2. Again, if you're not familiar with it, go back in a previous video of mine on annihilators, or look at read your book. But d squared minus 2d, if I took the second derivative of this, minus 2 times the first derivative of this, and then plus 2 of this, you'd get 0. I promise you. Okay. And then from this, I can jump right to what the particular solution is going to look like. The form of the particular solution. D squared minus 2d plus 2, not only does it annihilate e to the x sine x, it would also annihilate e to the x cosine x. So a particular solution will have some linear combination of those. A times e to the x sine x plus b times e to the x cosine x. All right. And then I'm going to find what are the value of this a and b, and then I'll have the complementary function, the particular solution. All right. So I'm just kind of saving some time here, skipping over some steps, but I did all the steps in the first 3 examples, so hopefully this will be a little easier. So I take yp prime, and really, I guess I'll just leave it like this. So we have a e to the x cosine x, that's first times the derivative of the second, plus second times the derivative of the first, so plus a e to the x sine x, plus, and then minus b e to the x sine x plus b e to the x cosine x, right, using the product rule. And then putting some stuff together, the e to the x cosine x stuff. So we have a plus b times e to the x cosine x. And putting the e to the x sine x stuff together, we have plus a minus b e to the x sine x. All right. And I'll take the second derivative, and I'll pause it and come back when I have it all, save some time for you. Alright, so a lot popped up on the screen. I took the first derivative, second derivative, and then subbing into the original differential equation and combining terms with e to the x sine x and combining terms with e to the x cosine x would yield the following. I have 3a e to the x sine x plus 3b e to the x cosine x equals, and then remember the expression on the other side was e to the x sine x. And then equating coefficients, 3a must be 1, right? the coefficients of e to the x sine x, and 3b must be 0. So a is a third, and b must be 0. So my particular solution, right, that yp, is just simply 1/3 e to the x sine x. All right, plus 0 e to the x cosine x. And now that I have the complementary function, the general solution to the corresponding homogeneous, and a particular solution to this equation, we can now state the general solution to this differential equation. Y equals, the complementary solution, right? Some constant c1 times e to the x cosine of 2x plus some constant c2 times e to the x sine of 2x. There's our complementary function, and then plus the particular function, the particular solution that we found to this equation, 1/3 times e to the x sine of x. Right, and there you have it. All right, so that one I kind of, I skipped over some steps because again I've done a bunch of these, and hopefully after seeing the first 3 examples you understand how I could find the form of the particular solution pretty quickly by knowing the annihilator of the right side. Alright, if you know the annihilator of the right side, you could jump to the particular solution form pretty quickly and then go about finding the constants. But you could also go through the entire process, all 4 parts of it. That can't hurt either. Right? The more you practice that, the better you get at it. So I'd recommend going over all 4 steps for however many, several examples. Try doing the same examples over and over again until you get them down pat, get the procedure down, understand the process. And hopefully, watching me cover these 4 examples in this video helps you out when you're going about doing problems similar to this, on your own. And thank you very much for watching.